Hello everyone, welcome to Adson Engineering Academy. It is me, your tutor, Adson. Today we're going to handle a new topic, that is shear force and bending moment. But before I continue, I would request you that please do subscribe to Adson Engineering Academy so that you don't miss any of my videos. Well, so let's dive into the detail of this particular topic, shear force and bending moment. First of all, let me define the two terms. Shear force is the algebraic sum of all the vertical forces at any section of the beam, to the right or to the left section. Well, if for instance this is my simply supported beam and I cut it into two, this is the left side and this is the right side, okay? So the forces on this side, the summation of vertical forces on this side, remember this is downward and this is upward, so the summation of forces on the left or the summation of forces on the right, okay? This summation of all this, the algebraic sum of all these vertical forces at this section is what we call the shear force. Shear force on the left or shear force on the right. Now, the second term is bending moment. Is also the algebraic sum of all the moments, not forces, okay? All the moments acting to the right or to the left of the section. You know very well that if you have a force if you multiply with what? The distance, let's say L, this gives you what we call the moment. So the summation of all this moment on the left or on the right of the section is what we call bending moment. Well, so let me take you to our next step, that is what we call shear force and bending what? Moment. So, moment diagrams. No, I'm just defining for you because this is introduction to this topic. So, the shear force diagram is the one which shows variation of shear force along the length of the beam. Okay, so if for instance you have a beam like this, okay, if this is our beam just like the first one we had, so the shear force diagram would show the variations, how the forces, okay, how the shear forces are varying along the entire length of this beam. Okay, so we shall see in the next video how to draw what we call this shear force diagrams. Okay, well, the second thing is also bending moment diagram. The same way is the one which shows variation of bending moments, okay, along the length of the beam. So the variations in the bending moments along the length of the beam is shown in what we call bending moment diagram. Let us continue to the next thing, and that probably is what we call type of the beams, because we are saying variation of shear force and variation of bending moment along the along the length of the beams. What are the different types of beams that we have? First of all, we're starting with the first one. Just looking at this, you clearly know that this is what we call a cantilever beam. A cantilever beam. Okay, so if this is a cantilever beam, what makes it a cantilever beam? A cantilever beam is a beam which is fixed at one end and free at the other end. Then we go to the next one, which is simply supported beam. Simply what? Simply supported. Okay, simply supported beam. Supported beam. So this is simply supported because at both ends we have a support, and this support is, one is hinge support, then the other one is roller support. So when you see a support like this, this is what we call simply supported beam. Now, if for instance I have this one, this is what we call overhanging beam. Simply supported, when it's having some part of it on one side protruding or even on both sides, we call it overhanging. Overhanging beam. Overhanging beam. Well, you see that this is overhanging because it is a simply supported with some part overhang. This is the part that makes it to be overhanging beam, this extra part protruding. Okay, so these are the three types. We still have two more types, that is to say a fixed beam and a continuous one, which is they're here. So this is what we call a fixed beam. What makes it to be a fixed beam? A fixed beam is actually a beam that is having what? Fixed end on both sides. Both sides are casted into the what? Into the wall. For instance, if this is the beam and these are the wall, so both ends are casted into the what? The wall. So you see, it makes it to be called what? A fixed what? A fixed beam. So let's look at this last one. This last one is what we call a continuous beam. A continuous beam continuous. Okay, so what makes it to be called a continuous beam? It is because it's having more than 2 supports on the span. So a beam with more than 2 supports is called a continuous what? A continuous beam. Well, after knowing the 5 types of beams, let me take you through also what we call the types of loads. So loads, in this case, if I have for instance a load here, this is what we call a point load. Point what? Point load. Another name can be called concentrated what? Concentrated load. This is very important to know that if it is acting at a point like this directly, it's a point load. What about the second one? The second one is what we call UDL. UDL in full is uniformly distributed load. Okay, uniformly distributed load. Okay, UDL. And then lastly is what we call uniformly varying load, UVL. Okay, this is what we call uniformly varying what? Varying load. So these are the 3 main types of loads that we have. Most importantly, what you need to take from this part is we need to understand how to convert UDL and UVL to point load to make drawing bending moment diagram very easy. You need to understand. You have to convert this UDL to a point load to make the calculation very easy. We shall see in our next video how to do this calculation. But to simplify it, allow me make it clear to you. If for instance the entire span is L, then this one is also L. How do I convert this what? And this UDL is W. Okay? Then this one is also what? W maximum at this per unit length at this point. Now what happens is that if I want to convert this UDL into a concentrated what? Load. Okay? So this is this UDL value W multiply with the what? Multiply with the span L. So it will become what? WL. You get it? So this WL is now what? Acting as a point load. But at which point do you have to put it? It acts as a point load at the center. If it is simply supported beam, it acts at the center of the what? Of the beam. So concentrated load will now become WL. So it acts at the center. This is L by 2. This side is L by 2. So this is how you convert UDL to a point load. Then secondly, what about in a uniformly varying load? How do I convert it to a concentrated load? So if this is uniformly varying, it is forming a triangle. So just simply get the area of the triangle, which is half times length, which is L, then this W. Okay? So that means this will become what? WL by 2. Okay? So this is now a concentrated load or a point load. But where is it acting in the beam? So since it's a triangular loading, it acts at 2/3 of L. 2/3 of L from this smaller part. Then from this bigger part, it acts at 1/3 of what? The span. 1/3 of the span. So you need to know where to put this what? This WL by 2. So this is how we convert a UDL and UVL to a concentrated load. It is very important. It will help us in our next calculation. So take note of that. Then lastly, in this video, let me show you what we call sign convention. So here is what we call sign convention for shear force and bending moment. Now, if this is, for instance, simply supported beam with load P. Okay? So a simply supported beam with load P, if I cut at this point, you realize that first of all, this load was supposed to be shared here on these 2 supports, P by 2. Okay? We shall see it how to do it. But if this is shared like this, you realize that if I take a section X at this point, so at this part of the beam, there is P by 2, which is going upward. And since the sign convention in this case says that if it is going upward, if that is the beam, okay, and this side is going upward, this side you take this shear force to be positive. If it is going downward, you take this shear force to be what? Negative. That is the sign convention for the shear force. Okay? But in this case, like for instance, in this case, this is going upward, this side is going downward, so it's taken as what? Negative. If the all of that section was, if it is cut from here. So if the all of that section, this is positive, then this P would be what? negative. But what about for the bending moment? A bending moment, for instance, like this, what you're seeing, the inner part is what we call concavity. Okay? Concavity. Then this outer part is what we call convexity. Now, if the concavity is on the upper part of the beam, like this one, this is what we call positive bending moment. Okay? Positive bending moment. If the concavity is on the upper side of the beam. But if the concavity, you can see that the concavity, this one is down. So this is concavity. So if the concavity is on the downer part of the beam, this is taken as a negative bending moment. Well, just to clarify it, you know, for instance, if you have a beam like this force will make the beam to bend like this. And if the beam bends like this is what? Producing concavity on the upper side of the beam. Concavity. And it becomes what? A positive bending moment. So for this case, this is positive bending moment. Okay? So you need to know that in any structure. Then this other one, when the moment is causing the beam to bend like this is called a negative bending moment. Yeah, so this has been the introduction. In our next video, I'll show you the steps to draw the bending moment diagrams and do the calculation. Thank you so much for watching this video till the end. Please do like the video, share, comment, and above all, subscribe to this channel so that you don't miss any of my video.